Tired of hearing it? Reality isn't real. Particles don't exist until you look at them. The universe is just a giant illusion, and you're the projector. Wave function collapse, observer effect, consciousness creating reality. It all sounds profound until you really think about it. What if it's not the universe that's broken, but our interpretation of it? What if the wave function collapse isn't some magical switch triggered by your gaze, but just a symptom of human limitations? In this video, we're tearing into the heart of quantum mysticism. We're not here to mystify, we're here to demystify, to question what's really going on beneath the math and whether this whole observer creates reality mantra holds any actual weight. Because maybe reality doesn't care about you watching. Maybe it never did. Let's find out. In traditional quantum mechanics, particles like electrons or photons are described by a wave function, a mathematical entity that encapsulates all possible states a system can be in. It doesn't just say where the particle is, but where it might be, with probabilities attached. Before measurement, the system exists in a superposition, a ghost-like blend of all outcomes. It's not in one state or another, it's in all of them simultaneously. But when we measure it, we're told the wave function collapses into one definite result. This idea was solidified by the Copenhagen interpretation, spearheaded by Niels Bohr and Werner Heisenberg. It suggests quantum systems don't have definite properties until we observe them. That measurement literally defines reality. Suddenly, the act of looking becomes sacred, but this raises strange implications. Are we to believe that an electron doesn't have a position until someone checks? That the moon doesn't exist unless it's being watched? Quantum theory may be powerful, but these interpretations take us into philosophical, even mystical territory. Here's where the cracks start showing. The Schrödinger equation, the engine of quantum theory, describes a smooth, deterministic evolution of the wave function. Everything proceeds according to well-defined mathematical laws. But then comes measurement, and suddenly, everything changes. The collapse is instantaneous, random, and irreversible. Unlike the rest of physics, it isn't governed by any equation, it's just assumed. You get one result, and all others vanish. But why? Why does measurement cause this break in the rules? More crucially, what even counts as a measurement? Is it when a person observes it? When a camera records it? When the particle hits a wall? The theory doesn't say. It leaves a gaping hole in the foundation. This is known as the measurement problem, and it's one of the biggest unresolved puzzles in quantum mechanics. Without a clear definition, collapse becomes a metaphysical patchwork, not a physical explanation. Now for the controversial take. Maybe wave function collapse is an illusion, not a real physical phenomenon, just a limitation of how we perceive and interact with reality. This idea is backed by decoherence theory. When a quantum system interacts with its surroundings, photons, air molecules, or even nearby atoms, it becomes entangled with them. The system's wave function doesn't collapse, it just spreads out into the environment. This spreading destroys interference patterns. It makes superpositions impossible to detect. To us, it looks like the system collapsed, but in reality, it's still in a vast, entangled state. It's like trying to read a message on a wet newspaper. The ink is still there, but the clarity is lost. We can't track the full wave function anymore, so we assume it's one state. But that's just our ignorance talking. Collapse isn't a physical process. It's a convenient fiction that hides the messy truth, that quantum systems never really choose. We just lose track of their complexity. You've probably heard of the double-slit experiment. It's the poster child of quantum weirdness. When electrons or photons pass through two slits, they don't behave like tiny balls. They form an interference pattern like waves. This implies they travel through both slits simultaneously. But when you place a detector at the slits, the pattern vanishes. The particle seems to choose a slit as if it knows you're watching. Many interpret this as proof that observation changes reality. But that's not quite right. The act of measurement introduces decoherence. The particle becomes entangled with the detector. It's not awareness that causes the change, it's information flow. And in the delayed choice quantum eraser, we even choose after detection whether to see the interference pattern. This has led people to think that decisions in the present affect the past. But that's a misreading. These are statistical correlations, not retrocausality. No message travels backward in time. Quantum experiments confuse because we ask classical questions of a non-classical world. If collapse feels forced, it's because there are other ways to explain quantum phenomena. The many worlds interpretation suggests all outcomes happen in separate, branching universes. When you observe a result, you don't collapse the wave function. You simply follow the branch corresponding to your outcome. Everything else continues just out of reach. Bohmian Mechanics proposes that particles have definite positions at all times, guided by an invisible pilot wave. The wave evolves smoothly without collapse. It's deterministic, but with a hidden layer we can't access. There's also relational quantum mechanics, which claims that quantum states aren't absolute, they're relative to the observer, but not in a mystical way. It's about relationships between systems, not consciousness. These interpretations preserve the math of quantum theory while ditching the need for mysterious collapse. They show that we can describe reality without elevating observation to divine status. Let's ground this in something familiar. Imagine flipping a coin, but you're blindfolded. The coin lands heads or tails, but you don't know. It has a definite outcome. Your lack of knowledge doesn't mean the coin is in both states. Collapse assumes that until you look, reality hasn't decided. But what if that's just human arrogance? Think of fogged glasses. You can't see clearly, but the world is still there. Quantum mechanics isn't vague because reality is uncertain. It's vague because we're limited in what we can measure. Wave function collapse was a useful crutch when we didn't understand quantum theory. But we've outgrown it. Decoherence explains how the illusion of collapse emerges. Alternative interpretations show collapse isn't necessary. Experiments don't require observers, only consistent rules. And philosophy warns us not to turn physics into a self-centered myth. Reality doesn't need you to see it. It never did. Thanks for watching. If this changed how you view the quantum world, share it. Challenge the assumptions. Subscribe for more science that breaks the mold.